Okay, so let's get going and see. And I'm going to try and make it a little bit more interactive. I mean, more writing based. And I mean, interactive for me means I'm not going to use the deck of slides. I have a deck of slides. I don't know how many slides there are. 50 slides, I think, probably. So we'll use some of this, but I hope you have had a chance to read through it. I don't know how much you could understand from it, or if you have seen PDs, it's great. I hope it was at least a bit of a refresher. So I'm going to start by focusing on this a little bit. Okay, so I'm going to do this again in notes. Whether you've read it or not, I'm going to talk about the 4 fundamental subspaces in linear algebra, and that's where we'll take it from. So this is what I mean by I'm going to make it a little bit more writing based than just with the deck of slides. So I have already added this pre-reading notes, but I'll add these slides that I have as well. Okay. So let's begin by some linear algebra that I couldn't get to the other day. And one of the things that I want to talk about, I'll see if this fan will work. Okay, it's okay, never mind. So hopefully the screen was visible. Let's start with, I think Ramanathan did mention, and you all folks agreed, that Gilbert Strang's linear algebra lectures and his linear algebra textbook are pretty popular ones, are like one of the standard references people use. I am personally not, I prefer using another linear algebra book, not Gil Strang's. Gil Strang's is generally, the taste is more engineering friendly, so I can see why it's popular. But there's one idea that, as far as I know, no one else does justice to it as much as Gil Strang does, and that idea is these 4 fundamental spaces in linear algebra. So I had already written a note about it in the pre-reading material, but I'll just quickly touch upon this here. Okay, 4 fundamental spaces in linear algebra. And it's going to slightly tie up with what I was talking about at the very end of my first day's lecture. Okay, so here is a linear map. We know now, let T from, let's say, from Rn to Rm be a linear map, and we know now that such a linear map, because Rn and Rm have standard bases, there is a matrix representation. Let A, I will call it A instead of T, because T's are somehow used as standard symbols for linear maps. PQRS is usually used for linear maps, and matrices are like A, B, C, D, and so on. Okay, so let A be the matrix representation of it. Okay, so I'm going to diagrammatically illustrate it as, that's my Rn, that's Rm. So if I want to sort of show that they are not really the same space, I might show it a little bit differently. So let's say I draw Rm like that. Okay, so that's my matrix A, taking Rn to Rm. Okay, then the 4 fundamental subspaces, if you have read the notes, you probably already know this. The 4 fundamental subspaces are the image. So let me write it as A, the image of this transformation, the linear transform, which I can define to be all y in Rm such that y equals Ax for all x in R in Rn. Yeah, so that's the image of, I mean, yeah, I could have just written the image is Ax for all x. Okay. Okay. So that's my, oops, let's say that's image of A. And then there is kernel of A, which is all x in Rn such that Ax is equal to 0. Okay. So that's something that is going to sit here. So that's my kernel of A. Okay. So as a remark, clearly 0 is in the kernel. The 0 vector in Rn is in kernel of A, okay, because A times 0 is going to be 0. If 0 is the only vector, is the only element in kernel, we would say that the kernel is trivial. Okay, otherwise it's non-trivial. Okay, cool. So if you folks have read the note, what are the other two fundamental subspaces? Okay, so for the sake of everyone, he said image of A transpose, which you could write as all x in Rn such that x is equal to sum A transpose y for all y in Rm. Okay. And so that means the A transpose is going to be some map from here to here, and this is going to be my image of A transpose. And likewise, there is kernel of A transpose. Okay, so kernel of A transpose is all y in Rm such that A transpose y is 0. Okay, so those are the 4 fundamental subspaces. But what is important or interesting or never, I mean, generally in most linear algebra courses that I know of, people don't talk about these 4 fundamental spaces for whatever preference, choice of textbook that they use, whatever it is. As far as I know, they generally don't mention it. This, if I taught a linear algebra course, at least an advanced course where I don't have to define vector spaces and so on, I would start with this at pretty early on. Okay. So the question though here is, this part is fine. Okay. So A is fine, kernel of A is fine, image of A is fine. Where did A transpose come from? Okay. And you'd know what the working definition of A transpose is. You take the columns of A and make it into row. But that's a very bad way of introducing what this A transpose is. Yeah. So it's not, you should in fact, if you have been thinking of A transpose as take the rows and flip them to make columns or whatever, equivalently columns and make them rows, I would recommend that you forget that definition from here on and try and use this definition as where A transpose comes from. Yeah. So where does, again, this was in my notes, so if you have read it, you probably know what the answer is. So where does A transpose come from? Where does this linear map, which is going to be a linear map from Rm to Rn, so A transpose is a linear map going the other direction. So it's from, in this case, Rm to Rn, because my A is from Rn to Rm. So in order to define this, you need an operation or an operator called an adjoint, and A transpose is just the adjoint in finite dimensional vector spaces. Okay, so we'll say this comes from defining what an adjoint map is. And this definition can be generalized, and I'm not going to tell you what it means to be generalized, but I would just say you can generalize it to infinite dimensional vector spaces, more generalizations of infinite dimensional vector spaces, which are, we'll just leave it there. Yeah. And in the finite dimensional case, reduces to the transpose. So it reduces to the transpose. You have to understand under the matrix representation, which assumes some basis. Okay. So if it's Euclidean spaces, you use the standard basis. If it's some other abstract space, you'll have to write down the basis using, you have to write down the matrix form and so on and so forth. There's something, but let's work with this really simple setup of the picture I drew first. We'll restrict ourselves only to Rn to Rm. Okay, no abstract spaces. Okay, so I'm going to tell you what is the definition of the adjoint map. So definition: adjoint of a linear map. So linear map means linear transformation. So all these are to be thought of as being the same vocabulary for, different words in the vocabulary for the same thing, okay, which is a linear transformation or a linear function or a linear map. And the linear map, although I haven't written it down, is between finite dimensional vector spaces, or you can generalize it to abstract finite dimensional vector spaces or abstract infinite dimensional vector spaces and so on. Okay, but in this setup, we are doing the simple case. Think of this as T from Rn to Rm. And since I want you to think of this as in the background, I'm going to make this gray color. Okay, so that's what you're going to think of when we think of this. So the definition is for such a T, I'm not going to write down all the verbose things. The adjoint map, which you can show is linear, which is denoted T star. So this is the notation. Is defined to provide this equality. So I take the inner product of Ax with y and demand that it be equal to the inner product of x with the adjoint of y. Okay, so just to recall, here means the inner product of Ax and y, and since we are in the Euclidean space setting, this inner product is the standard inner product. Okay. Okay, and so So let's do a quick consistency check. Okay. So, and I have to still, so is defined to provide the following. The adjoint map is the one, I should say, or maybe is defined as that, is the adjoint map T star is the linear map that provides the following equality. For this equality is not for a specific choice of x and y, for all x in Rn and y in Rm. So that's crucial. It's not for some random choice of some single like basis choice or something like that. Although you could do this via basis, yeah. So you'll do it. You'll need it for all choices of all x and y in these spaces. Okay. So consistency check. So x is in Rn. Ra is a matrix that takes Rn to Rm. So maps vectors in Rn to vectors in Rm. This means that A is going to be a m cross n matrix. Yeah. And so Ax, I mean, we already defined it, is going to be in the image of A, which is going to be a subset of Rm, and Ax is just going to be is a m vector. Let me write it like that. Okay. So Ax is going to be an m vector because you can check this, right? It's m cross n multiplying n cross 1, so it's a m vector. Okay. And thus this inner product makes sense, right? Is y transpose Ax, and each of these is a Rm vector. So you can take the inner product. So this is just a simple consistency check, the equivalent of dimensionality check or arguments from dimensions that you might have learnt in physics or engineering. So this inner product makes sense, and likewise the other inner product will also make sense. Yeah, I'm going to just say likewise x comma a star y will make sense. But technically these are two different inner products, right? But this is an inner product in Rn. So if you want to be precise, to be precise rather, we should define the adjoint as requiring this equality Ax comma y in Rm. So I can put a little thing to show that this is an inner product in Rm equals y comma a star x, sorry, x comma a star y in Rn. Okay, so it's important to note those are two different inner product spaces. Okay, both are Euclidean inner spaces and they have the standard inner product. But if you want to think about generalizing it, this should be the inner product in the right hand side space, and this is the inner product in the left space, where left is in and right I mean in this context, right, where the map is from which space to which space the map is taking, like, is defined. Okay, so if you now use this definition and you just do the algebra of it, you know, so performing the algebra, Ax can be written something like Aij. So I'm going to think of how I think of Ax. I'm going to show it to you once. I tried to show it on the first day as well. I'm going to think of it as x1, x2, xn, and I'm going to think of each column of A as something like this. and there are n columns because A is a m cross n matrix. Each column is going to be an Rm vector. So this each column is an Rm, but there are n of these columns, and I think of matrix vector product as this scaling this column, this component scaling this column, and then summing it all up. So this is going to be summation xi ai. I goes from 1 to n. If I pick this ith column, I could maybe think of it as 1i, a2i, a, that's a 2, ji, and ani. Okay. So if I want to write this down, therefore this is going to be summation I goes from 1 to n xi times a1i, a2i, a mi, my bad. Okay, and then you do the so you get the idea. Then y transpose ax is going to be summation yj axj for j goes from 1 to m now, because y is a m vector. And you can do this. I'm going to not try and do this. So you'll need to. It's a painful waste of and like a little bit of time consuming computation. You put this in, and you can then you'd get something like double summation aij xjyi, something like this. You need to verify this. It's not very important precisely how you end up, what you end up. And the other direction, on the right hand side, you would on the right hand side we would get inner product x comma a star y is going to be a star y transpose x, which can be thought of as being just x transpose. You could have done this right from here, but I wanted to do the gory version of it. So let's not do equals x transpose a star y. You go through this, you'd get something like a double summation aij star I think xjyi or something like this. Okay, you need to double check it, and from these two this is how you would conclude that aij star is aji. Okay, and then you define this to be the transpose of the matrix. Okay, so that is a star is a transpose. Okay. It's okay. You can fill in the details. This is the rough idea. There might be some algebraic errors. You can do an even more direct argument, but I'll leave it to you to go look up Gilström or wherever online. So it's the precise details are slightly less important for us. It's just that this is where you get the transpose idea from. Okay, shouldn't think that the transpose comes by just transposing the rows and columns of the matrix. The transpose is the adjoint of the linear map expressed in the matrix form. Okay, so if the original map has a matrix representation A, the adjoint has a matrix representation which we are now so familiar and call it A transpose. Yeah. Okay. Notice to define the adjoint, I need an inner product. Okay, so I can't define an adjoint in that abstract Euclidean space that I called En. Okay, you need the inner product to be able to define the adjoint map. So transpose does not even make sense unless you have an inner product. So in Euclidean setting, there is a standard inner product. So people normally don't pay close attention to it, but you need an inner product on a vector space if you want to generalize this to be able to define what the adjoint map is, and therefore in this Euclidean setup to define the transpose. But that's not the takeaway. The takeaway is to define the adjoint, need inner product. It's like ingrained in the definition of the adjoint. And once you have an inner product, you have a norm. So inner product spaces have a natural norm. And at the end of my first day, I was trying to sort of drive this idea that norms and inner products provide geometry to the Euclidean space. Yeah. So thus geometry is needed. Okay. So this is important. We'll keep this in mind. We'll come back to it again today. But right now we'll understand that geometry is needed for defining inner products. And how does it manifest itself? So this is so geometry is not merely measuring the lengths of vectors or their angles. It manifests quite nicely in this diagram itself. It manifests. Anyone knows the relationship between these four fundamental subspaces? Image of A and kernel, that okay, that's one thing that comes out of it. Okay, there is a direct decomposition, so I'll write this down. There is a direct some decomposition, but I'll just say direct decomposition. Rn is image of A transpose plus kernel of A, and Rm is image of A plus kernel of A transpose. Okay, you can show that every vector in Rn under this has to be a combination of a element in kernel of A and image of A transpose. But okay, that's one observation, but the geometry comes from right. So providing the inner product and defining the adjoint gives us the following relation. Image of A is, let me write it like this, is orthogonal to kernel of A transpose. So if I want, I can I don't remember how so in the notes, if you take a look, I try to show it in a slightly different way. I drew the picture a little bit differently. Let's see if I can quickly go back to it by the time it warms up. I hope you folks didn't bring your computer. So in the illustration in the notes, I try to show this by putting this little right angle thing between the spaces to show that these subspaces are orthogonal to each other. Orthogonality is a geometric concept, and it could not have come up, you couldn't have talked about all this without having inner products, which induces norms also, of course. But geometrization of the Euclidean abstract vector space gives us notions like this. Yeah. So I'm going to go back to my iPad. So in linear algebra, the notation for this would be to say image of A is kernel of A transpose perp. Okay, that little thing is called perp. Okay. And on this side, of course, kernel of A is going to be the image of A transpose perp. Okay, and technically I need a parenthesis, but it makes, you have to make meaning of this in the way that it naturally makes sense. So if you want, I can put this parenthesis. The perp is not for the operator, but it's for the space. Yeah. But it should be evident even without writing that parenthesis. Okay. So that's a simple proof. So I'm going to write this down here. So short exercise, verify, prove, whatever, that kernel of A is image of A transpose perpendicular, and image of A is kernel of A transpose perpendicular. Okay. Okay, so let me just go back here. This means, this orthogonality means if I take A and obtain a vector, it will be in the image of A. I can now, so I can do the following. So I can say x is equal to ay. Oh, sorry, let me write y equals ax. And because of this orthogonality, I can write z equals A transpose y. I will not get a 0 in this case. Yeah. So I can, once I go this way, I can come back by operating on the y that came from doing ax. Okay. So is that okay? So let's define the following. Let's define, and I'll try and put a small picture of this. So A, image of A, this is kernel of A transpose, this is image of A transpose, and that's kernel of A. Okay. So if I take an element that's in the kernel, I mean, of course, it's already going to be killed, it's going to become 0. But for anything that's not in the kernel, let us define for any x not in the kernel of A, the matrix, call it delta, as A transpose A. Okay. So it's not going to be in the kernel. So let me try and see if I can draw a better picture here. So in order to define this, it cannot be in the kernel of A. So we are going to try and gray that out. So it's not in the kernel of A. We'll leave that out. So I have a point x under A. It goes to image of A, somewhere in the image of A. Let's call it y equals ax, and we know that this cannot be, this is not the kernel of A transpose. So I can try and gray it out with a different gray, and so I can bring this back via A transpose. Okay. So we can call this matrix, we shall call this matrix written as delta. Some of you already know that what it's going to be called, because the theme of today's talk is Laplacian, and you might have seen Laplacians being represented by the letters delta, symbol delta. So we'll call this as the Laplacian in linear algebra. Okay. What is the purpose of defining anything? I don't know how many of you folks follow the Hank brothers on YouTube, who run a bunch of different things. Originally started as Vlog Brothers. Then they have SciShows, they have the crash courses. Crash course in any subject is run by the Hank brothers. One of the Hank brothers wrote, I think, no, Green brothers, not the Hank brothers, excuse me, the Green brothers. One of the Green brothers wrote Fault in Our Stars, which was a popular little young adult novel, made into an English movie, made into a Hindi movie. I don't know, in Tamil they made such a movie in 1987 itself, with Mani Ratnam directing it, but it's just a universal theme. So they have this little, it's a very popular YouTube channel. I don't know, Gen Z does YouTube, or I don't know what you folks do, you just do Insta Reels or Snapchat, I don't know. But recently, one of the Greens, I think it was John Green, not Hank Green, John Green tried answering a question his nephew asked, which is, why does anything exist? Yeah. And he has it's a 5-minute video. I would recommend you go watch it. But it's in the same spirit. Why define anything, right? But to tie it back to what I was saying, if you adopt this purely mathematical approach, you can define anything and try and show a bunch of properties. That mathematicians would be happy doing that. Yeah. So we have defined a Laplacian matrix. I can now try and see what properties it has, and then I could refine my splitting of those spaces. There's something called as harmonics. I'm not going to talk about it. You can show a bunch of things, and then you can show that this matrix is positive, semi-definite with a sign. If I threw in a sign, and so on and so forth, I could do many things. Okay, but if you're an engineer or a physicist or a science person, you might say, why bother, right? So the reason is, it turns out that the Laplacian operator that we all might have heard of models a bunch of physics phenomena, which therefore is useful for engineering. And in a solid modeling kind of a course, that physics phenomena which was useful in engineering can also be adopted for doing interesting things with your solid models, like smoothing functions on the meshes that you saw for like the Stanford bunny, for instance. Or you could just smooth the bunny itself. There might be some application or something like Ramanathan was talking about it, right? Like, if I give you a point cloud, how do I know what shape is it? Okay, you could probably put a shape on it, but that shape may not be very nice looking if you built it using Delaunay triangulations or Delaunay tetrahedralizations. You might want to try and smooth things out a little bit. So there are applications. So we'll look at a few applications if possible on the demo hands-on. But the idea is, again, is that in physics, you notice there are certain things you can model with certain mathematics. Heat flow, for instance, or the field produced by a point charge in space. All these can be modeled using the Laplacian operator. And what we have done is we have abstracted it out. There's a Laplacian operator, which I'm sure you all know what it is, d square over dx square, which was there in my notes as well. So what we have done here is we have simplified our life even more, right? We are looking at the Laplacian, we are starting it out by looking at what it is in linear algebra, yeah, which is usually a good place. You should first crawl before you walk, and then before you run, you need to walk, and so on. So it's like we defined it here for the purpose that it's useful in some other context, and this is the simplest version of it. Yeah.